Okay students, so let's resume our discussion. So till now we were discussing about memory chip, right? And we were discussing that like each memory chip can be designed in two ways, like byte addressable and word addressable. And this byte addressable is nothing but when we predefine size of cell to be 1 byte. Okay, so byte addressable memories are nothing but those memories which have predefined size of 1 byte of cell. Okay, the size of the cell will always be 1 byte for byte addressable memories. Okay, similarly when we have this word addressable memories, word addressable memories have predefined size of cell being 1 word. Okay, so size of each cell in word addressable memory will always be 1 word. Okay, we have also discussed what a word is. A word is a fixed size data that is considered as a unit by the processor, right? So basically each processor, like while fetching the data from main memory, it fetches only 1 unit of data at a time, right? So that unit of a data is called as word. Okay, now you must be having this question, what exactly this addressable means. What is this addressable, right? So okay, so CPU eventually fetches the content like instruction and data from main memory, right? Now if CPU wants to fetch the data, it must know the location where content is present, right? For example, we have a main memory here and content is present somewhere, right? And CPU wants to fetch value. For example, if it wants to fetch value 5, it must know where exactly this 5 is located in main memory, right? Therefore we need some kind of indexing mechanism which helps this CPU to point out the data it wants to get from main memory. Okay, so this indexing mechanism is actually called as addressing. So this indexing mechanism is called addressing. Just a second. This indexing mechanism is called as addressing. Okay, now addressing basically means assigning a unique index to all the atomic entities in main memory. So what is the atomic entity in main memory? Cell, right? Cell is the atomic entity in main memory, right? So we will be having unique index assigned to each cell. Each cell we will have a unique value assigned to each cell that we call as address. Okay, so we will call this value to be the address of that cell. Okay, and this unique value will always be a binary number. It will always be a binary number. Okay, because CPU is again a digital device, main memory is a digital device. If CPU wants to locate some address, it will send this information in binary numbers. So that is why address is always defined in binary numbers. Okay, okay, so let's take an example of main memory. Let me give you an example of a main memory. Let's erase this. Let's take an example of a main memory which can store 128 bits of information. The capacity of this main memory is 128 bits. Okay, and let's suppose this memory is byte addressable. So what do you mean by byte addressable? That means each cell will have the capacity or size 8 bits, okay, and so on, right? That means there will be total 128 divided by 8, that is 16 number of cells, right? There are 16 number of cells in this main memory, right? So if we want to represent each cell in binary, so this 16 is nothing but total addresses, like this will have one address, this will have one address, this will have one address. So 16 cell means that we require 16 addresses, 16 unique addresses, 16 unique addresses, and these addresses must be binary in nature, right? So can you tell me how many bits are required to represent each cell, like how many number of bits can we use in order to make these 16 numbers? Yes, it is log 16 base 2, right? Log 16 base 2 is nothing but 4 bits. So if we have 4 bits, then we can represent 16 numbers, right? If we have 4 bits, we can represent 16 numbers ranging from 0 0 0 0 to 1 1 1 1, right? If you have some understanding of integer to binary representation, like conversion, you must be knowing that this value is 0 and this value is 15. So from 0 to 15 there are 16 values, right? So we will be requiring 4 bits, okay? We will be requiring 4 bits in order to represent an address, okay? Now these 4 bits are called as address bits, okay? These are called as address bits, okay? So now we are using these 4-bit sequence to represent each cell, which is also called as the address of that cell, okay? So this is exactly the same example as this diagram here. So this diagram is having 16 cells and each cell has size 8 bits, okay? So now let's talk about the main memory representation. So we have a representation for each memory chip. Like if we have a memory chip, how can we represent that memory chip? Okay, so there is a standard way to represent each memory chip, and this representation looks like number of cells cross the size of each cell, okay? Number of cell cross the size of each cell. Therefore, for this 128 bit memory, and this memory is byte addressable memory, we will be representing this memory as 16 cross 8 bits, right? It will be represented as 16 cross 8-bit memory chip, okay? It can also be represented as 16 byte memory, right? Because 8-bit is 1 byte, right? 16 byte memory, okay? I think this is clear, okay? Now what is the benefit of representing the chip like this? What is the benefit? So there are there are many benefits, there are many things that we deduce out of this representation. So what are all those things that we can deduce out of this representation? Basically we can deduce 3 things, okay? 3 things. One is parameter 1, that is number of cells, that is address space, okay? Here 16 was our address space, that means there were 16 number of cells, okay, in this example. The second thing that we will deduce is the size of each cell. If we have something like this, if we are told that we have 16 cross 8 bit memory chip, then we can say that address space in that memory chip is 16 and size of each cell is 8 bit, right? 8 bit. So using these two information, what is the thing that we can deduce? What is the thing that we can deduce? Since the entire memory is divided into cells and each cell has some capacity, so if we do the summation over the capacity of all the cells, we will be having the capacity of entire memory chip, right? We will be having the capacity of entire memory chip. That means if we multiply, let me use another pen. So if we multiply 16 and 8, like 16 number of cells and each cell has 8 bits, then we will be saying that the capacity of this memory chip is 16 cross 8, that is 128 bits, right? The capacity of this memory chip is 128 bits. Okay. This is the third thing that we can deduce out of these two informations. Okay. Now using these, one of this information, we can also deduce number of address bits that are required. We calculated this already, right? We calculated this already. So we know if we want to calculate the number of address bits, what we will do? We will take log of address space base 2, right? Address space is nothing but number of cells, right? Number of cells base 2 log number of cells base 2. This is the number of address bits. Okay, we will be having the number of address bits after calculating log number of cells base 2. Okay, I think this is clear. One more thing which must be which we must remember here is that I have to erase these things. Okay, so one more thing that everyone should be remembering here is each cell in a memory is associated with two operations. Like for example, this is a cell, right? So a CPU, since it is a supervisor, a CPU can perform two operations in every cell. One is a read operation, one is a write operation. So a CPU can do or can perform two operations, either one of them on any cell, and therefore we have this read and write operation defined for each cell in a main memory. Okay, so each cell in a main memory is kind of associated with these two operations. Okay, so I think this is clear. Now we will be understanding more about the actual circuitry inside the main memory. Like for example, if CPU wants to access main memory, it will give some things, right? So how these things are like going inside a circuitry, and that is how we are the main memory knows whether we will be performing some read operation or write operation on any particular cell, and on which cell we are performing this read and write operation. This all information will be covered, like we will discuss all these things when we will be discussing memory organization. Okay, we will be discussing the entire organization of main memory in our future classes. Okay, so for now I think this is since it is an introductory class, This is all we will be discussing, like for a main memory. This is all you need to know for now. Okay, so let's proceed. So till now we have briefly discussed IO devices and main memory, right? Now we will be discussing about system bus, okay, or system interconnection. So what is system bus? System bus is nothing but a set of conducting lines. It is set of conducting lines. It is set of conducting lines that are used as a shared transmission media between different components. Okay, shared transmission media between different components. Okay, so we have given these two components here, like CPU and memory chip. So this entire part is called as system bus. Okay, this entire part is called as system bus. This system bus is nothing but set of conducting lines. Okay, so now you must be having this question, what exactly is a conducting line, right? So conducting line, as we understood in physics, conducting line is a line that lets the electricity pass through it. That means we can generate, or we can create some potential difference between the two ends of this line. Okay, so it is nothing but a line. So for example, this is a conducting line, right? So it is a line through which electricity can be passed. Okay, so now we want this conducting line to transmit some information, and that information will be either 0 or 1. So one more thing, each conducting line, let me write it here, each conducting line will be used, will be used to transmit one bit of information. Okay, each conducting line will be used to transmit one bit of information, and that's it. One conducting line can transmit, can send, or can receive one bit of information. Okay, this is one thing that we know. The other thing that we know is conducting line is the one which can pass the electricity through it. That means it can create a potential difference, it can support a potential difference at the end of this line, at the two ends of this line. Okay, now since we know that it will be transmitting one bit of information, that means it will be either sending or receiving 0, or it will be sending or receiving 1, right? It will do either one of these two things, right? It will be sending or receiving 0, or it will be sending or receiving 1. Therefore we want to discretize the state of this line, right? So since we know this line, or a conducting line, can be in two states, right? In two states, when the current is flowing through this line and when the current is not flowing through this line. So what we can do is, we can assign two states as 1 and 0. Like we can define, if a current is flowing through this line, then we can say for example, if we are assigning the current flowing, the state when the current is flowing through the line being 1, when we assign the state of conducting line where current is flowing as 1, then when the current is flowing through this line, we will say that this line is transmitting one bit of information. Okay, so we can just assign the two states, current either flowing or not flowing, as 0 or 1. Okay, now the definition of 0 and 1 depends on the type of pin. So actually a processor, so this is a CPU, right? So each processor or each device, like memory is also having pins, right? So each processor will have some number of pins. Okay, and one pin is mapped to one line. Okay, and the definition of 1 or 0 depends on the type of pin the line is attached to. So for example, if this CPU is having a pin, this pin, I'm so sorry, let me, this is a pin on which this line is connected, right? This is some conducting line which is connected to this pin in CPU, right? And this pin is active low pin. Okay, if this pin is active low pin, that means whenever, that means this pin will be sending or receiving bit value 1 when no current is flowing across the line. Okay, whenever no current is flowing through this line, we will be saying that this line, I mean this pin is sending or receiving one bit of information, bit value 1, one bit of information it will be sending or receiving, but that value is 1. Okay, value of that bit is 1. Similarly, if there is active high pin, there is one more terminology, like for example, this is a pin and this conducting line is connected to this pin, and this is CPU's active high pin. Okay, so if this pin is active high pin, in that case if CPU wants to send or receive bit value 1, if it wants to send bit value 1, if it wants to send bit value 1, what it will do, it will pass a current through this conducting line. Okay, that just means that it is transmitting one bit of a bit of information, that is 1. Okay, the value is 1. Okay, so I think this is making sense. I hope this is making sense. So there are different type of pins, like active high, active low. There are various type of pins. We will discuss all types of pin in a dedicated session for system bus. Okay, we will be having a dedicated session for system bus where we will be discussing all these type of pins. Okay. So let's continue our discussion. So we were discussing system bus, right? Should I erase anything? Okay, let it be. So system bus, what is system bus? System bus is nothing but a set of these conducting lines. These are conducting lines, right? These are conducting lines, these are conducting lines, these are conducting lines. So system bus is nothing but set of conducting lines which are used as a shared transmission media between two different components. Okay, and the number of bits that can be transmitted in one go depends on the number of lines in the bus, which is also called as size of the bus. So for example, this is a system bus, right, between CPU and memory chip. So what is the size of this system bus? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So size of system bus here is what? 50, right? Because it can send or receive 15 bit of information at one go. Again, actually it depends on the lines, but for now let's suppose the size of system bus is combinedly 15. Okay. Now we can further classify this system bus into three categories. Okay, now we will be discussing what I was just saying that it all depends on the type of lines. Okay, so basically this whole system bus is classified or categorized into three things, and it is this category, like this classification is based on the kind of information that is transmitted through them. Okay, so let's understand these categories with an example. Okay, so you know that CPU is a supervisor. I am saying this multiple times, but again you should like kind of by heart it, right? CPU is a supervisor, right? We know that CPU is a supervisor, and it is the one who accesses the content of main memory, right? We have this example here, CPU and memory chip, right? And for example, CPU wants to fetch instruction that is present in address 5 of main memory. Okay, let me give you an example here. Let me erase everything. Okay, let me erase everything here. Let me give you an example. Okay, so suppose CPU wants to fetch the instruction that is present in address 5 of main memory. So there is some cell whose address is 5. Okay, and in address 5, in cell with address 5, we have an instruction I. Okay, we have an instruction I, and CPU, what it wants is it wants to fetch this instruction from main memory. Okay, so what all things it will do? So in order to fetch this instruction, CPU should be able to unambiguously specify what it wants, right, to the main memory, right? Therefore it will tell two things to main memory. What it will tell? It will tell that I want to read an instruction, right? What I want to do? I want to read an instruction, right? CPU will say I want to read an instruction. What is the other thing it will say? It will say this instruction is present on address 5. It will say the instruction which I want to read, this instruction is present on where? On address 5, right? It will be saying these two things, 1 and 2, and this command will be kind of unambiguous, like it will be specifying what it wants and how it wants, right? Now this second information about this address, will be sent by the CPU through some dedicated lines. Okay, so eventually CPU will use system bus in order to inform these two things to main memory, right? It will be using system bus to inform this information, these two things to main memory. Okay, so how will it do that? It will use the address lines. In order to tell the second thing. Okay, what is the second thing? The second thing is he wants the instruction which is present on address 5, right? So he will be sending address 5 on address line. Okay, now how is this 5 represented? Like in binary, if you know binary conversion, you must be knowing that 5 is represented as 101, right? 101, 1, 2, 4. I think you must be knowing that. Okay, so since there are 4 lines here, we can add 1 0 here. Okay, so what we can do here, we can put 0 here, we can put 1 here, we can put 0 here, we can put 1 here. Okay, and here memory will know that since 0101 is coming from address lines, that means this is some address. This is address of a cell. Okay, and this is address of a cell on which CPU wants to do something, right? Now the first thing is the first thing that CPU wants to tell to main memory is, I want to read an instruction, right? Now this is reading an instruction is a signal which specifies what type of operation will be performed by CPU on this particular cell, right? On this particular cell, address 5 cell. Okay, cell with having address 5. Okay, and CPU will send this information through control lines. It will send this information through control lines. For example, this line is dedicated to read signal. Like if we pass some current, if we send a bit 1 through this conducting line, for example, this conducting line is kind of assigned to a read operation, then it will see that 010 is here, right? And this 010 which will specify that 010 here will specify that CPU, sorry, it will specify that CPU wants to do read operation, right? Simple. And in return, what main memory will do? Main memory will send this instruction which is present on address 5 within this memory. It will send this instruction via some set of lines. Now this set of lines are also dedicated. Now this set of lines are dedicated for sending data or instruction. Since main memory has only 2 things, either data or instruction, so there is a dedicated line, there is a dedicated set of line which will be sending either instruction or data to CPU through these lines. Okay, and these lines are called as data lines. The lines on which address is sent is called address line. The line on which the lines on which the data is sent either from main memory or from CPU is called data lines, and the lines on which the control is sent, like the type of operation is sent, the information about the type of operation is sent, are called control lines. Okay, I hope this is clear. Now these are the 3 type of buses. So these are nothing but these lines cumulatively are called as bus. Okay, address lines are nothing but address bus. Data lines are nothing but data bus. Control lines are nothing but control bus. Okay, I think this is clear, right? We can proceed. Okay, let me erase this. Okay, one more thing that I want to discuss here is I think you might be noticing something here. Okay, if you are able to notice one thing, I have made address line as unidirectional. That means this is directing towards main memory. This is directing towards main memory. That is, information will always be sent from CPU to main memory, right? And therefore these lines are unidirectional. Why is this? This is because these addresses will always be sent by CPU and never main memory. Why? Because these addresses are of whom? These addresses are of cell, and these cell are present where? These cell are present in main memory, and CPU is the one, again CPU is supervisor, right? CPU is the one who will be performing any kind of operation on any cell of main memory, right? So he is the one who will be saying that I want to perform XYZ operation on this particular cell in main memory. So to specify that particular cell, it will be sending the address of that cell through address line. There is no need that main memory will be sending any kind of address to CPU, and that is why address bus is always having unidirectional lines. Okay, all the lines in address bus will be unidirectional in one direction, and that direction is from CPU to main memory. Okay, similarly data bus. Now data bus is kind of different. Like here we can see data bus are having bidirectional lines, right? That means CPU can either get the information or CPU can send the information. Now what is information? Information is nothing but data, right? CPU can either get this information or it will send the information, right? And when does CPU do that? When does CPU do that? CPU receives the information or data or instruction. Like information is nothing but data or instruction, because memory is having instruction or data only, right? So CPU will be getting the information when CPU performs a read operation. Okay, and CPU will be sending the information, like storing some data into main memory whenever CPU is doing write operation. Okay, so if CPU is doing read operation, it will be getting the information. If it is doing write operation, it will be sending the information. Therefore the data lines are always bidirectional. Okay, the data bus are having bidirectional lines. Okay, address bus is done, data bus is done. Now control bus. So control bus is kind of little bit different. Control bus will be having both the things. It will be having unidirectional lines as well as bidirectional lines. Okay, it will be having both the things. Okay, so yeah, it will be having both the things, because sometimes we will be sending some information, like we will be sending some signal, like kind of operation which we want to perform. And for example, either instead of memory, IO device is present here. So I think you all must have heard about interrupts, right? So interrupt can come from IO device to CPU, right? Now this interrupt is nothing but like interrupt is one such example, right? So this will be also called as, the control bus will be also called as partly bidirectional lines. Okay, that means the lines in control bus can be either unidirectional or bidirectional, some combination of that. Okay, I think this is clear. I hope this is clear. Okay, okay. Now one more thing which I want to discuss here is okay, let's discuss. So you must have, like, since we studied memory representation here, like there are two parameters to represent any memory. Okay, so what would you like say about this system bus, this exact system bus? Like for this particular example, what would you say? You should say that this system bus, the system bus in this diagram, supports memory chip of size 16 cross 8 bit. it will be supporting memory chip of size 16 cross 8 bit. Why is that? Because since each cell is having 8 bits of information, the data lines will be the number of lines in data line will be 8, right? 1 2 3 4 5 6 7 8, right? So we have 8 lines in order to send one bit from each line, okay? And since we have 16 number of addresses, and we also know that 4 bits are required to represent 16 addresses, right? To represent 16 addresses, we need 4 bits. Therefore, address bits are 4. Therefore, here we can see that there are 4 lines, right? Because each address here will be comprised of 4 bits, right? 4 bits from 0 0 0 0 0 0 0 to 1 1 1 1, right? So if we want to take, like, if we want to get the, like, if you want to read the cell whose address is 0, we will send 0 0 0 0, right? So this particular system bus will support 16 cross 8 bit memory chip, okay? I think this is making sense. I hope this is making sense, okay? You must have also heard someone saying like CPU XYZ supports at max of 16 GB of RAM. Like, you must have heard that, right? CPU XYZ supporting, for example, 16 GB of memory or RAM. Let's say RAM, okay? 16 GB of RAM. What does it mean? We already discussed that each CPU or each processor have a set of pins, right? Set of pins. And each CPU has some pins assigned as, like, dedicated to address bus, some pins dedicated to data bus, and some pins dedicated to control bus, right? And these number of pins are defined, these are predefined, right? These are manufactured, right? So these are predefined. So we can just connect these many number of lines, because each pin can be connected to only one line, right? Now what do we mean by CPU XYZ supporting maximum 16 GB of RAM? Okay, so let's proceed let's proceed step by step. 16 GB of RAM, what does it mean? For example, this, since it is represented something like this, B means byte, that means it will be byte addressable, okay? So this particular RAM is byte addressable, okay? That means there are 16 giga number of addresses, okay? 16 giga number of addresses, number of cells, 16 giga number of cells, okay? What is giga? Giga is nothing but 10 to the power of 9, right? It is 10 to the power of 9. I'm so sorry, it is 10 to the power, just a second, it is 2 to the power 30, okay? It will be more clear why I am saying that, because we are representing a memory, and memory is normally, like, we can see byte here, right? So byte is always this 10 to the power something, 10 to the power 3 is 1000, but 1000 is not equal to, like, we always say 10 to the power 3 is almost similar to K or kilo, but in case of memory it is not same. Here K is 1024, so that is why I am not taking 10 to the power 9, I am taking 2 to the power 30, okay? Just a second. Yeah, okay. So G means 2 to the power 30 and 16 means 2 to the power 4, right? 2 to the power 4 into 2 to the power 30, that is, there are total 2 to the power 34 number of cells in this RAM, okay, and the size of each cell is 8 bits, that is 1 byte, okay. Now in order to represent 2 to the power 34 number of cells, how many number of address bits we require? We will be requiring log 2 to the power 34 base 2, that is 34 address bits. We will be requiring 34 address bits in order to represent any cell, okay. That means our address line should be having 34, like our address bus should be having 34 lines, right? So CPU must be having 34 pins, right? CPU must be having 34 pins. If we have, for example, 32 GB of RAM, then we will be requiring 35 address bits, right? And since we have 34 pins, it is not supported by this CPU, right? That is why we say this CPU can support at max of 16 GB of RAM, because it has 34 pins for address, okay. I think this makes sense, okay. So whenever you hear someone saying CPU XYZ support at max of alpha GB of RAM, now you know what exactly it means, okay. You must have also heard about a processor being 32-bit or 64-bit, right? You surely must have heard about this, okay. Now 32-bit processor means it has 32 data pins, okay, and that means there are 32 data lines that are connected to CPU. There are 32 data pins which are connected to 32 at max 32 data lines, okay. And now if we can get or send, like fetch or send at max 32-bit of information, what does it mean? It means, as we discussed, size of one word here is 32 bits. Size of one word here is 32 bits, because we can fetch 1 unit of information at one time, at that one unit of information here is 32 bits. We can fetch or we can send 32-bit information at one go. That means the size of word is 32 bits here, okay. So a processor being 32-bit means the word size for that processor will be 32-bit, okay. That means there are 32 data pins, okay. If the processor is 64-bit, that means processor has 64 data pins, okay. That means the word size for that particular processor is 64 bits, okay. I think this is clear. So again, there will be a dedicated session for the system bus as well, where we will be seeing what are the different ways, like in which a system bus can be designed between like CPU, main memory and IO devices, okay. We will be having that dedicated session in like upcoming classes, okay. So you need not worry about that, okay. So this is about system bus. So now let's move on to the brain of computer. What is the brain of computer here? CPU or processor. CPU or processor here is the brain of computer, okay. this is the place where actual processing happens. Okay, and as we discussed, CPU fetches instructions, right? I've said this multiple times, I've said this so many times, but I will say this again. As we discussed, CPU fetches instructions, right? And these instructions were getting executed by CPU magically till now, right? We discussed that CPU will take one instruction, execute it, then go to another instruction, execute it. So this execution part was a magic to us, right? So is CPU a magician? No, obviously not. CPU is what? It is it is a component, right? And we are the one who designs CPU, right? So we surely are not magician. That means CPU is also not a magician, right? Therefore, there is an explanation to everything that happens inside this CPU. We will understand this entire execution process in our upcoming class, so no worries. Okay, we will be having this entire execution process, how execution happens within a CPU. We will discuss everything about that. Okay, so first thing first. Okay, now first thing first, this is a CPU, and a CPU is logically divided into two parts. Okay, it is logically divided into two parts: data path and control unit. Okay, now like similar to a brain, CPU performs two major tasks. What are those two major tasks? One is processing, second is controlling. One is processing, second is controlling. Okay, now processing involves performing some operation. For example, like person X, you remember person X? Person X gave this add 5 to CPU, right? Now ALU is some component which is also called as arithmetic and logic unit. It actually does the operation, this addition operation. So processing involves performing some operation, and that operation will be done by some component like ALU. Okay, now do you remember when we were building this computer for person X, right? So what we did, what we were we also designed the processing logic, right? Let me go there as well. It might take some time, but yes, we also designed processing logic, right? We designed processing logic, and I also told you that this processing logic will be hardwired where? In CPU. Now we are discussing CPU, right? Yeah, now we are here. Okay, so now this processing logic is usually hardwired in CPU itself, and that too in the form of circuit. Okay, so this processing logic is hardwired in CPU. Okay, in the form of circuitry, so we will be having circuit, an entire circuit which will represent the logic, the processing logic. Okay, now the hardware circuitry that is dedicatedly doing the processing is called as data path. This circuitry is nothing but data path. Okay, that eventually means that data path does processing, right? Data path does processing. So data path is doing processing, and this circuitry basically contains three components. Data path contains three components: CPU registers, ALU, and CPU interconnection. Okay, now this CPU interconnection is nothing but the wiring part in a circuit. Okay, but again it is very important, we must be having this wiring part. Why? because it is the one which actually helps combine different properties of these components. So we have this register component, right? We have this ALU component, but this wiring is the one which actually combines the property of these components in order to perform a certain operation, right? This wiring is the exact logic, right? So the wiring is very important. So CPU interconnection is the wiring part in a circuit in data path. Okay, now this is data path. This is all about data path. Now what is the second thing that brain does? Like we discussed processing, right? The second part is controlling. Okay, what is controlling? Controlling involves managing all the components to perform a certain operation. Okay, data path has the potential to process, okay, but it will process based on the controls, like there is a control unit, right? Control unit eventually does this controlling part. It will do the controlling part. So the hardwares that are dedicated towards controlling all the operations are called control unit. So what I am saying here is, for example, what controlling here means is, for example, if we want to perform some addition operation, if we want to perform this addition operation, then in order to perform this addition operation, one signal will go to ALU component through what? Through control unit. Control unit will send one signal to ALU component, and it will kind of instruct ALU component to perform addition operation, right? It is a controlling unit. It controls everything inside data path. Okay, how the processing will happen. This part is the controlling part, okay, and control unit does the controlling part. Okay, let me give you like a daily, like a corporate environment example. So in a corporate environment, we can consider data path to be the technical team. What is data path? Data path here is technical team. It is technical team, whereas the control unit is managerial team. Okay, control unit is managerial team. Okay, now this technical team always has this potential, like it can do certain tasks, but this task should be assigned to them, right? Now the control unit, that is the managerial part, managerial team, is the one who assigns these tasks to team members of this technical team, right? So if we want to perform some task, control unit or managerial team will be assigning this task to each of the team member of technical team or each of the components of data path. Okay, so in short, data path is the one doing the processing, whereas control unit is the one which will tell what all components combinedly will be doing this processing. Okay, whether we will be using ALU, whether we will be using register R1, or we will be using register R2, or we will be using, for example, if we want to fetch an instruction, what all registers will get activated. So that particular instruction or signals, like to activate, will come from control unit. Okay, okay, so now let's I think this is all right. Like CPU is logically divided into two parts, data path and control unit, and we will be having a very like descriptive detailed discussion on data path as well as control unit and all the components here, like CPU registers, ALU, CPU interconnection, everything. Like control unit, we will be having a very kind of detailed discussion about all those things here. But for now, this is all like this is kind of the larger view of what CPU does, what CPU has and what CPU does. Okay, so I think this is clear. Let me erase this. Let's continue our discussion. Okay, so I think till now you must have seen this small unit here which is called as clock. This clock was also present in structure of, just a second, sorry, this structure of computer. It was there, right? This clock was present there. I discussed 4 major components here, but I didn't discuss clock here. But I told you that there is one thing called as operating speed, right? I was discussing operating speed here, but I told you to wait. We will be discussing the operating speed in a while. Now let's discuss operating speed. Okay. So yes, so since we are discussing CPU here, so let's discuss operating speed with respect to this device, like CPU. Okay, we are since we are discussing CPU, let's discuss this operating speed in context of CPU. Okay, so you can see the clock here. Okay, now this clock is attached to CPU. Okay, and this clock is actually oscillatory in nature. What does it mean? It means that this clock ticks on regular interval of time. So it will tick on regular interval. Let me not write something here because I have this color scheme for everything here. Okay, so we can see like this is kind of the signal which keeps on happening. This is the kind of signal which oscillatory clock will make. It ticks on a regular interval of time. Okay, so now if our clock follows this routine, this regular interval of tick, then it will change its state in some interval, right? Now this clock tick here can be considered as clock changing the state from 0 to 1. Okay, okay, so let's remove this part. Let's concentrate on why do we need this clock, right? This is the major question, right? Why do we need this clock? Now this clock is set in such a way that the smallest unit of processor activity is carried out in one tick. So for example, this is clock tick, and for example in one tick it is changing from state 0 to state 1. In another tick it is again changing from state 0 to state 1. Then whenever like this state changes from 0 to 1, we consider that to be tick. Okay, this is T1, this is T2. So there is some time between T1 and T2, right? Now this is called a time between two ticks. Okay, now a clock is set in such a way that a smallest unit of processor activity, processor does some activities, some very basic activities, some basic operations, and these basic operations, very small operations, are performed or are carried out in one tick, in this small time, in this one tick, in this small time. Okay, therefore the time difference between these two clock ticks is the time taken by one processor activity. This time T2 minus T1 is the time taken by one processor activity. It is the time taken by one processor activity, one processor activity to get completed, okay, and this is nothing but clock cycle. It is called as clock cycle. This entire part, this from here to here to here to here, this is a clock cycle, or this is a clock cycle. Okay, this is a clock cycle. Okay, This is clock cycle, and this clock cycle tells us how fast an operation is performed, because clock cycle is nothing but the difference between two ticks, right? Now this difference between two ticks is also a time, right? So this time tells us how fast an operation is performed by CPU. Okay, hence the operating speed of CPU. Simply put, this is the operating speed of CPU. Since only simple commands can be carried out in each clock cycle, most of the CPU processes that it does needs multiple clock cycles. Okay, so one such simple command, like simple processor activity, is fetch operation. For example, CPU, when it does fetch operation on main memory, this is kind of one processor activity, and this can be done in one clock cycle. Okay, so this is one example of one processor activity. Okay, but most of the tasks are not done in one clock cycle. There are multiple clock cycles that are required to process to do these CPU processes. Okay. Okay, now let's discuss operating speed or clock speed. Okay, now operating speed or clock speed of a processor is like a way to measure the performance of CPU. So this operating speed, okay, let's not write it here, let's use another page, right? Operating speed or a clock speed, it is also called as clock speed of a processor, is a way to measure performance of CPU. Okay, it is a way to measure the performance of CPU. Okay, now let's see how to calculate this performance. Okay. Okay, so let's start our discussion with speed. Okay, so we all have learned speed formula in our physics class, right? Now what is speed? Speed is basically what? Speed is distance upon time, right? That means it is the distance traveled in 1 unit of time. For example, 1 second. Okay, in 1 second, distance traveled in 1 second is called speed. Similarly, operating speed, as the name says, is number of operations upon time. It specifies number of operations performed in 1 second. Okay, it is the number of operations that are performed in 1 second. That is called operating speed. Again, speed and operating speed are kind of similar, but yeah, yet very, very different. Okay, I'm just giving you a reference of what operating speed, how can we calculate operating speed. Okay, now we know that speed has this unit, right? Meter per second or kilometer per hour, right? Similarly, operating speed also has one unit. Now this unit is hertz. Okay, and 1 hertz means 1 operation per second. Now if we have operating speed to be 1 hertz, that means 1 operation can be performed in 1 second. Okay. So yeah, this is operating speed. This is used to measure the performance of CPU. Okay, now for example, if you want to measure the performance of a mobile, okay, for example, you have iPhone 12. Okay, you have iPhone 12, so you must have seen that iPhone 12 has iPhone 12 has 3.1 gigahertz processor, right? Oh, sorry. Yes, i12 has 3.1 gigahertz processor. What does it mean? It means that the operating speed of processor of i12 is 3.1 gigahertz. Again, we discussed giga, right? Giga can either be 2 to the power 30 or it can be 10 to the power 9. Okay, whatever suits you best, you can just imagine. Okay, you can just imagine that it says, this thing says that i12 or iPhone 12 can perform 3.1 into 10 to the power 9 operations per second, and that is very high number, right? That is very high number. 3.1 into 10 to the power 9 number of operations per second is very high number, right? So this is kind of operating speed of a CPU, right? That is why we say, we told you, I told you that this CPU is kind of the most, like having the most the highest operating speed. The operating speed of CPU is more than all the other components. Okay, CPU has the highest operating speed. Okay, you got an idea here. Okay, now we will be discussing like all the components of CPU, like data path, what all things are there in data path, what is CPU register, what type of CPU registers are there, what is ALU, what is like CPU interconnection, how can we design a data path, what are control unit, what all things are there in control unit. All these things, all the components of CPU will be discussed in much details in our upcoming classes. Okay, so let's proceed. So previously we saw a logical structure of entire computer, right? Like this was, you must have seen, like I shared this structure of computer here, right? Yes, structure of computer, right? This particular image is like a logical structure of entire computer. Okay, logical structure of entire computer. Now that the problem there was, each component there was like a black box, right? We don't know how these black box work. Okay, and what is inside this black box, we didn't know that. Now this is also the structure of computer, but this one is more informative structure of computer. Okay, and it contains all the things, like it has all the four components. It has processor, it has data lines, sorry, it has system bus, I'm so sorry. It has processor, it has system bus, it has input output device, IO device, and it has main memory. It has all four components, right? IO interfaces connected in between IO device and processor. Okay, so we discussed all of these here, right? All the things here, how main memory looks, how processor looks. Processor is ALU, registers, control unit, right? And we also saw that there are different type of IO devices and IO interfaces required to do many things. Like there are many functionalities of IO interface. That is why we use IO interface in between IO devices and processor or CPU, right? So this is kind of the structure of computer, where the logical structure of each component is present. Now each component's logical structure is present here. Okay, Now what we can do here is we can quickly dry run 2 CPU operations on main memory. Okay, we can perform 2 CPU operations on main memory. What are those CPU operations? There are just 2 operations that a CPU can perform on main memory. What are those? Read operation and write operation, right? These are only the 2 things that a CPU can perform on main memory, right? Now let's start with read operation. Okay, if CPU wants to read a value 4 that is present on second cell, this is second cell, right? This is second cell. Now we can see here 100, right? 000 something like that, and 100, right? Again, this memory is byte addressable, right? This memory is byte addressable. This memory is byte addressable. Okay, so this is 100 here. That means the value that is on this address is 4, right? Now if CPU wants to read this value that is present on second cell, what will it do? It will send, what it will send? It will send this address 0001 on address line. It will send 0001 on the address line. Okay, it will send this 0001 to main memory via address bus. Okay, and the second thing that it will do is it will send read signal. For example, this is the conducting line or the line which specifies whether we need to do the read or not. So for example, we are sending 1 here. Okay, that means we want to perform read. Okay, so we will send read signal to main memory via control bus, right? We are doing that. We are sending address, we are sending the signal which specifies the exact operation to be performed, right? Now CPU will receive value 4 through data line, right? Main memory will send this value 000000100 through data line, right? So this is how CPU will get this particular data, value 4, right? Value 4 is what? A data, right? So we will get this data through data lines. CPU will get this data through data lines. That is how CPU reads the value 4, right? That is present on cell 2. Now cell 2 is, like you can see here, cell 2 is represented by 1. One more thing, I mentioned it earlier as well, but again, addresses starts with 0 and goes all the way up to number of cells -1. Okay, that is obvious, right? It will go from 0 to number of cells -1. Okay, this is one thing you must remember. Okay, now this is read operation. We did the dry run for read operation. Now if you want to do write operation, what we will do? First we will erase everything. Okay, now we will do write operation. If CPU wants to write value 5, if it wants to write value 5 on where on main memory, it wants to write value 5 on main memory on fourth cell, on fourth cell, that is on fourth cell, that is 0011. This is 3, right? This integer equivalent of 0011 is 3, right? So on address 3, 012012 on this address we will be writing value 5. How will we do that, or how will CPU do that? CPU will now again send the address here 0011 via address bus. Okay, now it will send the write. For example, this conducting line was for write, so it will send 1 here. So for example, like if there is 1010 here will mean write. Okay, 0 1 here will be read. Okay, so for example, it is sending 1 from here, 0 from here. Okay, in that case it is a write operation. Okay, now it is sending this signal, write signal, from control lines or control bus. Okay, now it will send value 5 through data lines. CPU will send value 5 through data lines. What is the equivalent of 5? Like, how can we represent 5? We can represent 5 as 1 0 1, the remaining are 0, right? We will be writing this thing here, right? So this is 0 0 0 0 0 0 0 0 0 1 0 1, right? Okay, so now data lines will have 0 0 9, this particular value 5, right? And now main memory, after seeing the address line, it knows there is something, like CPU wants to do something on this particular cell, and after seeing the control lines or control bus, it also knows that he has to listen onto this data bus in order to write, because CPU want to write this information which he sends on data line to where, to this cell, right? So it will, what it will do, it will write 0 0 0 0 0 1 0 1 here. Okay, now this is how write will operate, write will happen. Now main memory will eventually main memory updated its value on 4th cell to 5. Okay, from some garbage value to 5. Okay, now this is write operation. We also did the try run for write operation as well. Okay, I think this is making sense to everyone here. Okay, I hope so. So this was kind of a brief introductory discussion. This was done to give you a very brief idea of how a computer looks and how a computer works. Okay, now in our upcoming classes we will be going quite deep into each aspect of what all things we studied today. Okay, now we will start our discussion in next class with data path. Okay, so till then, thank you.